All right, we're back. So now we will discuss right hand rule number 2. Just to make things easy for you, of course, nobody will ask you what did you use rule number 1 or rule number 2. And you don't even have to memorize how you do it. You just need to know how to use it. The first one is related only with two quantities or variables or whatever, current and magnetic field. The second one, and of course the third one, it's related with three variables. So this one is related with I and B, all right? And then we will find the direction of the force, which is perpendicular to both of them. If you see, this is the direction of the current, which is now not the thumb, it is your fingers. And then you curl towards the direction of the magnetic field, all right? Don't try to keep twisting your hand. You should not end up in hurting your hand. It should go easy. The fingers are towards the current, then they curl towards the magnetic field, and the thumb will be the direction of the force. So the thing that you have really to understand here, that the direction of the force is perpendicular to both of them. You see, either if you are here, you see this is perpendicular, or with the B, because B is out, right? So both of them, it means F is perpendicular to both of them, the I and the B. Good. So this is rule number 2. This is for a current which produce B, and this is the direction of the force, that is the magnetic field is acting with this force on this current. Great. Now, what about when we have a charge moving with a velocity v in the magnetic field B? Also, this is to find the direction of the force. Of course, here we're talking about positive charge. I will comment on that in a minute. So this is the direction of the velocity, which is the movement of the charge, with your fingers. Then you curl your fingers towards the magnetic field, and then the thumb will be pointing towards the force. Of course, thumb will not always be up, it could be down. All right, imagine that the velocity is in this direction, right? So if you curl, then okay, it means also the thumb is up. It depends. What if the charge is negative? If the charge is negative, whatever, you make something for the positive, everything for positive, and then you, of course, the direction will be opposite. For example, if the moving charge here is negative, then the force will be down. All right? All right. So this is for the positive charge, and if it's negative charge, then it will be the reversed direction. Okay, let's come. I'm going backward. Here it says the magnitude of the force is by the formulas, okay? While the right-hand rule is useful to determine the direction. The magnetic force is always perpendicular to the magnetic field direction. This is very important actually to remember always. Here it says things to remember, all right? So the magnetic force is always perpendicular to the magnetic field direction. So it could be a problem and it has numbers in it. Don't be fooled. Maybe he's just asking you the direction of the magnetic force or the magnetic field. So you should always make sure that you understand that the magnetic force is perpendicular to the magnetic field. All right, guys? equations are for magnitudes only. Good. Now let's go backward. What do you think about this backward thing? Is it flipping your head yet? Here. No, in this specific one, I will go to one step before because it's talking about the negative charge. All right? Okay, here. So this is about the force on the electric charge moving in a magnetic field, and we have explained this already. This is a positive charge moving with a velocity v in a magnetic field B, and this is the direction, again, between B and V. Okay, so this is the direction between the velocity and the magnetic field. And we have explained this already, all right? And this is just a simple example. It looks very complicated, but it's not. This is a North Pole, and this is a South Pole of magnets, different two magnets. Of course, the magnetic field, when you're supposed to read the section 1, you will know that the magnetic field lines goes from the North Pole to the South Pole. So even if the problem will not give you the direction of the magnetic field, here it's known that it's from north to south, north to south. So it is going to the right, for example, here. And let's just assume now that we are dealing with the positive charge Q, where the direction of motion, velocity, is to this direction, all right? So just with me, try to make your fingers towards the direction of the velocity and curl to the direction of the magnetic field, so you will realize that the force is up. While in the other one, the negative, immediately you don't have actually to curl or anything. Just you do it for the positive and you realize that force is up, so for the negative, automatically it's down. All right, guys? So you do the same thing. You don't have to start twisting your hand. V, and then you curl towards the magnetic field, and then you realize that the force is up, okay, because it is perpendicular. Actually, if I were you, I wouldn't even think much about it. F should be perpendicular to the B. But of course, we have to take care of the direction of the motion as well, because you need to really specify where is F, all right? So this is the right-hand rule. Okay, and here, this is another example. What is this? This is the blue. The blue thing is the direction of the magnetic field, and it is into the page. You know, this is into the page, this is out of the page. So it's into the page, and the velocity is to the right. Assume first of all that the charge is positive. So if we go with our fingers to the velocity to the right, and the magnetic field is in, so you can, I hope that you're doing it with me. My fingers are to the right with the velocity, and then they curl to inside the page, so you can tell that the force is upward, all right? Because I am assuming the charge is positive, yes, positive. While this is not a positive charge, it's an electron. So immediately you just say that the force is down, all right? What if the same problem, but instead of electron, we have a proton? What will be the situation? V is the same, and I'm telling you that B is the same, it's into the page, so the force will be just simply up. So you have to pay attention to this, to the charge. Is it positive or it is negative? All right, good. Let's go up, up. And this is back to our ILB, okay? And this equation will define the magnetic, this equation defines the magnetic field B, all right? And this is the magnetic force, and this is the electric current, this is the length of the wire, okay? The unit of the magnetic field is important because you have never taken it in physics 2, which is Tesla. All right, Tesla, it's not a familiar thing in SI units. And if you remember, in SI units, we have Newton, ampere, meter. Let's go back to the relation, and you will tell. It doesn't have to be memorized. ILB sine theta. Of course, this is without unit. This is the magnetic field. This is in Newton because it's force. This is current, so it is ampere. And this is the length, so it is meter. Now you can tell it's Newton times, sorry, it's Newton divided by meter divided by ampere. Now I think it makes it easier. Okay, we don't want the Gauss thing now. All right, guys. So I am done with the important stuff in chapter 20. Okay, let's do this for more practice about the direction. Okay, this is also F is equal ILB. And if you see F is perpendicular on the B, this is also a magnet. And as we say that the magnetic field is going from north to south, all right? And you see, basically it's perpendicular. The force is perpendicular to B. Even here, regardless why it's down, still force is perpendicular. Means in this situation, this is B and force is there. All right? And in this situation, of course, I have to mention them all with vectors. What about here? Magnetic field is here, but force is down, right? But both of them are perpendicular, regardless of the direction of F. So it's not enough only to know that it's perpendicular. You should know, is it up or down? That will be specified by the direction of current. Now go with me with the current direction. It's going this way. Just go with your fingers towards the current and turn them to the right, because that is the direction of the magnetic field. You will realize that the force is up. In A, go with your fingers to the direction of current and then curl them to the right, because that is the direction of B. All right? And you will realize your thumb will go down. This is important. How to specify the direction of force. It's up or down. Okay? Of course, how the current is created? By a simple battery. All right? That's how the current is created. Guys, it's nice to mention here, see how big is the voltage? It's 22. So don't expect this kind of effect to happen when we are using our simple 3 ampere or 1.5 ampere, and those simple currents maybe in the lab, you know, they will not produce this much kind of magnetic force on them. All right? Okay. And this is also a picture of if the current is going in this direction, then there will be a magnetic field. Basically, it all goes, like you see, his thumb is towards the current, and immediately the curl, this is right hand rule number 1. This is the picture for right hand rule number 1, okay? Number 1, which is only I and B. So if your thumb is going with the direction of the current, immediately the curl of your fingers will go to the direction of the magnetic field. So for example, here the direction of the basically the direction of the magnetic field is like that. Okay, it's going like that. Okay, because it goes with the curl. And this is right hand rule number 2, which is F, L, sorry, not L, I and B. Okay, and this is right hand rule number 3. Again, I am telling you, right hand rule number 3. Again, you don't have to memorize them. I just want you to know these rules. Guys, I am done. This is, you see, this is right hand rule number 1. Okay. Again, current is with the finger, with the thumb, and the curl is B. I am done with explaining chapter 15, guys. Sorry, 20, and 15 minutes are over. So thank you so much, and I hope that you understand the things that we've been through. We've gone through. Thank you so much.